Welcome to a tutorial of Proflan. In this particular video, we're going to look at how to answer question to do with motor effects. This is AQA physics past paper questions. So if you are going to do the exam, you need to understand how to approach different questions when it comes to this particular topic. And if you're new to Proflan YouTube channel, consider subscribing so that anytime I'm going to do more tutorials and more topics on AQA, you'll be notified. So we're going to dive in and to get started so that we can be able to see how are questions asked. For instance, here we are told the circle in the figure represents a straight line carrying current. Now we're supposed to draw how the magnetic field pattern is going to behave. So definitely whenever you see a cross, it means current is getting into the paper. But if you see a dot, it means current is getting out of the paper. Now since here we are having a cross at this particular point, it means first, since it's a conductor, it means we are going to have circular or concentric magnetic fields around. We are going to have circular magnetic fields around this conductor, but also you have to predict the direction of these magnetic fields because fields have got also direction. So you can be able to use right hand grip rule in order to predict this. And the way to do it, since current is getting into the paper, you assume that you are gripping this particular conductor like that, such that the thumb points where the direction of the field is going. Yeah, so the thumb points the direction of the current. So you are going to put your thumb like this. Let me just move the camera so that you can be able to see exactly what I'm trying to display here. I don't know whether you can be able to see it. Can you see it now? All right. Yeah, so let's check whether you can be able to see it clearly. Yeah, so you're going to place your thumb like that, such that the thumb points into the paper. So these fingers here will tell you in which direction is the fields going. So the direction of the fields will be in the clockwise direction like that. So basically that is exactly what we are supposed to do in this particular case. So that is how the fields are going to behave around that particular conductor using right hand grip rule. We need to move to the next question, and we are told that the magnetic flux density 10 centimeters from the wire is 4 microtesla. Micro means divide by 1,000. That's what we mean by micro. But at the same time, you need to understand that this is the same as 10 raised to power negative 3. So which means if we are talking about 4 microtesla, is going to be 4 times 10 raised power negative 3 Tesla. Yeah, so that's what we are going to have at that point, and then we are going to say the correct answer in this case is here. So we're going to tick this particular point there. Moving to the next question, let's see what is the next question that was tested here. We are told that we are having a simple electric motor, and this simple electric motor, there is a current flowing through. When there is a current, the coil rotates continuously. Yeah, so we are supposed to explain why does current when there is a current, the coil rotates continuously. So what you need to understand, when a coil is placed in a magnetic field, what is going to happen is that there will be a force on this particular coil, because when current flows through this coil, it means around the coil there will be magnetic fields, and the magnetic fields of the permanent magnet will interact with the magnetic fields which will be created due to the flow of current. So in that way, there will be a force exerted on the coil. So one end current will be flowing in a particular direction, and in the other end of the coil current will be flowing in the opposite direction. So for instance, in this case here we are going to have current flowing this direction, and also on this other side current will be flowing in this direction. So you realize that the two ends of the coil are going to have different forces, or the forces will be acting in opposite direction. So we are going to start by saying when current flows through the coil, the coil will experience forces due to motor effect. Yeah, so when there is a current in this particular coil, so we're going to say there will be a current. When there is a current in the coil, there will be a force experienced due to motor effect. Yeah. Yeah, so just adjusting this camera so that you can be able to see it well. I believe now you can be able to see it properly. Yeah, so the first thing, when there is a current, there will be a force in the coil. So each of the parts, because this end would experience according to Fleming's left-hand rule, so we are going to have fields, and then we have current. So this is going to experience an upward force, and this other end is going to experience a downward force. So we are having a scenario whereby we have forces acting in different directions. Yeah. The forces on the coil acts in opposite direction. Opposite direction, and this causes a turning effect. So the turning effect is as a result of the two opposite forces which will be acting in each of the part of the coil. And the reason as to why that is happening is because the current will be traveling in opposite direction in the coil. Yeah. After each half revolution, these commutators reverses we can also swaps. We can say swaps from one carbon brush to the other. And this reverses the current in the coil. Hence, the forces acting on the coil remains in the same direction. Remains in the same direction. So that's why basically we are saying that. Believe it's clear. So since the commutator are going to reverse the direction, they are going to swap as it rotates. This commutator that we have here will be on this other side and this one will be on the other side. So this is going to reverse the flow of current. Hence, the force experienced on the wire is going to remain the same and making the coil rotate continuously. Yeah, so making the coil to rotate continuously. So basically that's how you are going to approach this question of how a simple motor works. The only thing that you need to remember, where there is a current passing through the coil, there will be magnetic fields created around this coil. So these magnetic fields are going to interact with the magnetic fields of the permanent magnet, making this coil to experience a force. Since the current in the coil are flowing in opposite direction, here current is flowing this direction, here is current is going to flow in the other direction, then it will mean that these two coils or the parts of the coil are going to experience forces in opposite direction, and that is going to cause a turning effect. Yeah, so basically that is how you're going to approach such kind of question. So let's dive in so that we can be able to see in question 2 what we are supposed to say and how we are supposed to approach this one. Let's see what we can be able to do. Yeah, we are having a simple setup, very interesting setup. We have a magnet, and you see the magnet is going to provide the magnetic fields, and when there is a conductor and there is current passing through, then this conductor, when there is a current passing through the conductor, then we're going to have a magnetic fields created around the conductor. That magnetic field, due to the flow of current, is going to interact with the magnetic fields of the permanent magnet, and then we're going to have a force, and that is going to be motor effect. So let's look at the question that was asked. What is the name of the effect that causes X to move downward? X to move, the motion is due to what we have called motor effect. This is motor effect. Yeah, so this is motor effect. Suggest one change that will make the apparatus that increase the size of the force. The size of the force depends on these factors I'm going to mention. Number one, the amount of current. So suggest the change that will increase. The change will be increasing the current. If you increase the current, you are going to increase the strength of the force. And something that you need to remember, force due to the magnetic, the flow of current is going to be Bill. The formula for that is Bill. This is the strength of the magnetic field flux, and this is the current, and this is the length of the conductor. So which means that the force experienced, it depends on three factors: the strength of the magnet, the amount of current, and the length of the conductor. So also we can be able to say another aspect that can really affect this. We can talk of using the change, using a stronger magnet, using a stronger magnet. So if you use a stronger magnet, definitely you're going to increase the force experienced by these particular conductors. So maybe if you are told to explain how that happens, remember that whenever current flows through a conductor, there will be magnetic fields created around that conductor. When those magnetic fields which are created due to the flow of current interact with the magnetic fields of this permanent magnet, then the conductor is going to experience a force. Yeah, so basically that's what you're going to do. Let's look at the next question. The next question here says that the figure shows two small weights placed. We've answered, I think, all the questions here, so we can ideally move to the next part. We can now move to the next part. We have answered next question. Is there anything? All right, so the figure shows a small weight placed you don't wanna which one? You don't wanna? So we are having that gentleman is trying to come in for the lesson of physics. I think if I'm going to give baadaye iache nilie imalize, siko mlango okay, just relax here. Yeah, so now we are supposed to calculate. So the force experienced, we can be able to see the force experienced here. Just wait. Yeah, just wait. So the force experienced in this case here is 4.8, but remember force is equals to we said force is equals to BIL, whereby this is the magnetic flux, this is the current, and this is the length of the conductor. So wire X is 5 centimeters long, so we are going to say this is 4.8 times 10 raised to power negative 14. is equals to the magnetic flux is the one that we are trying to find. Then we're going to, okay, let's do this, huh? Right, hold this one, let's do it. So after we've just this one, like this. So let this guy now teach. The current is times 1.5 times the length of the conductor is going to be basically .05, because you have to convert this to meters for you to work it out. So then we are going to divide by 1.5 times 0.05 divide by 1.5 times 0.05, so that this guy and this guy will cancel out. Then we shall have our B equals to, we can just put this direct into the calculator so that we can be able to see what is going to give us. It's going to be 4.8 times 10 raised to power -4, and this is 1.5 times 0.05. If you just put that in the calculator, you're going to have that's going to be 6.4 times 10 raised to power -3, yeah, -3 here. So this is T Tesla, and this is 6.4 times 10 raised to power -3. So this becomes the final answer in this case. So this is what exactly you are supposed to do in a question like this in order to work it out. Yeah, so if you are new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. And also for you to be able to access the PDF of the worksheet that I'm working on here, you can be able to access it in our Patreon page. Just check the link in the description so that you can be able to access this. Let's go. Rose. I'm thinking you're going to trace me. All right, so we can now proceed to the next bit. I think I need to look for my pen, yeah, so that we can be able to. All right, so let's move to the next question, and this next question says, the figure shows a straight wire passing through a piece of card, and this is one of the methods you can be able to study the magnetic fields around a conductor. A hole is created, and then the conductor that is carrying current is passed through this particular card. You can see current flowing in that particular direction. Here current's going down like that. We are supposed to describe how you will show that the magnetic fields has been produced around the wire. There are two different ways you can be able to do this. Number one, you can be able to use plotting compass, or you can be able to use ion filings. So we are going to say you sprinkle ion filings on the card and tap gently. When this happens, when you do this, they will arrange themselves in a given pattern. So you're going to see the ion filings will form concentric circles like that. They will form very beautiful concentric circles like this, so which is going to represent the magnetic fields. So if you want also, you can be able to use plotting compasses. You place them different position at different positions. It will indicate that the plotting compasses will deflect, all will move, and that will be an indication and that will be an indicator that magnetic fields have been has been created. So there are two different ways you can be able to approach that. You can be able to use ion filings, or you can choose to use plotting compasses in that particular case. Right, so explain how the ignition circuit works. How does the ignition circuit work? Can you just write in the comment section, how does the ignition circuit work? After this video, I'm going to read through your comments so that I can be able to see what you have said. Yeah, so we are having different sections here. We have ion arm. We also have a pivot at this given point. So which means when this ignition switch is closed, current is going to flow. Yeah, when it's closed, current is going to do what? To flow through this coil. And the moment current is going to flow through the coil, this is going to become an electromagnet, which means it's going to pull the ion arm. It's going to attract, and the ion coil is going, the ion arm is going to be attracted towards this. The moment that is done, a gap is going to be created. The moment this ion arm is attracted, an arm is going to be what? A gap is going to be created here, and that breaks the flow of current. Again, it goes back, because immediately the current stops flowing, this stops being an electromagnet, then the ion arm is going to be retracted, or is going to be released. The moment it's released, again it's going to do what? Close the gap. Are we together? So basically the first thing we're going to say, let me see whether you can be able to see where I'm writing. I have to ensure I keep on checking this so that I can be able to follow through. Yes, so I think, yeah, it's okay now. Now, upon closing the switch, and that is, we are talking about closing. Upon closing, if you close this ignition switch, current flows through the electromagnet, through the coil. And it becomes magnetized. It becomes magnetized. The electromagnet attracts the ion arm. It attracts this ion arm. And when this happens, the ion arm pushes the contacts, pushes the, we can say, pushes the contact. Let me write it properly. And the starter motor circuit become complete, making current to flow through the starter motor circuit, making it return. Yeah, so immediately you close this switch, current will flow here. When this ion arm is attracted, it's going to make this to close. When this closes, it will mean current is going to flow through this particular section, which makes the motor to start working. And basically that's how this circuit works. Close, current flows. When current flows, this becomes an electromagnet which pulls the ion arm. When the ion arm is pulled in this direction, it crosses the contact here. Then when this contact is closed, it means that current can be able to flow through this section, so making this motor to start running. Describe how you will show the magnetic field has been produced. Already we have worked out this question. We have just answered it here. So we've just answered it in this section. So there is no need of repeating that. All right, so moving further to the next question. When the switch is closed, there is a current 2 amperes through the wire. The wire experiences a force and moves. Use the correct word from the box to complete the sentence. The demonstration show the motor effect. Motor effect. The 2 changes that the teacher could make to the demonstration, each of which will increase the force. Changes could be increasing the current. So if the teacher increases the current, in this case, we realize that we are going to have a bit stronger force. So basically, that's what we are going to mention here. Another aspect we said is changing the amount of the magnetic field. And in that case also, you can say using a stronger magnet. We can as well say using strong magnetic fields. Strong or increasing strength of magnetic fields. Yeah. State one change that the teacher could make to change the direction, reversing the direction of the current. And this can be done by interchanging the terminals, yeah? By interchanging the terminals. Yeah, so if the teacher comes and interchange this terminal, positive to negative, negative to positive, this is going to reverse the direction of the force. If the teacher is going to increase the power supply, increasing the current, it will increase the force experience. If the teacher comes and uses a stronger magnet here, it will also increase the strength of the force experience, because we said that force is equals to Bill. Yeah, this is the formula you can be able to use to calculate the force. If you take the magnetic flux times, magnetic flux is the strength or the fields is from the field. If you have a stronger magnetic flux, we are going to multiply it to the current times the length of the conductor, and in that way you're gonna earn max in that way. Let's see part D. With the switch closed, the teacher changes the position of the wire so that the force of the wire is 0. What is the position? What is the position when it's perpendicular? When it's perpendicular, in this case, we are going to say it's going to experience the strongest, but in this case, we're going to say when the wire is parallel to the magnetic field, there will be 0 force. Parallel to the magnetic field, we're going to have a 0 magnitude. Yeah. Let's see in question number 6, what is it talking about? Yeah, closing the switch creates a force that acts on the wire. Explain why the force acts on the wire when the switch is closed. Yeah. So, number 1, here we're going to say when the switch, let me see whether you can be able to see whatever way I'm writing. Yeah, when the switch is closed, current flows through the wire. When the switch is closed, that's when the current, there will be current between X and Y. So for instance, if we are having this as the current flowing here, we have also, remember, current to be flowing, and then at the same time we are having magnetic fields. Yeah, we are having magnetic fields. Yeah, so if we are having magnetic fields here, just use this color. We are having magnetic fields which are pointing from the north to the south, like that. So when there is a current flowing through the wire, around this wire there will be concentric magnetic fields which I created. So these magnetic fields which I created are going to interact with the fields of the permanent magnet. So in that way, there will be a current, there will be an interaction between two different magnetic fields. Now, for instance, if you're having a magnet and another magnet, if you bring them together, they are going to repel or attract each other. Same case applies here. If you're having two different fields, they are going to interact, and there's a pull and push that's going to be created. So when the switch is closed, current is going to flow. Yeah. As current flows, it creates magnetic fields around the conductor. Yeah, they create the fields due to current interact with the fields of the permanent magnet fields, resulting to a force. So if you've attended Proflan lesson, remember when current flows through a conductor, there will be magnetic fields created around that conductor due to the flow of current. And since we are having the magnets here, there will be also magnetic fields. When the two magnetic fields interact, there is a force created. This conductor is going to experience a force. And you can be able to predict the direction of the force by Fleming's left-hand rule. You can be able to use Fleming's left-hand rule to do that. Yeah. So the force causes the wire X to move. Draw an arrow on the diagram to show the direction which it's going to move. Yeah. So we are having the fields in this direction, and this is our positive terminal and this is our negative terminal, so meaning that current is going to flow in this direction, isn't it? Yeah, so let me just see whether you can be able to see where I'm drawing. Yeah, so can see here current will be flowing that direction, here current will be flowing, so in the conductor current will be flowing that direction. So which means if you use Fleming's left hand rule, you can be able to predict. So you can be able to put, this is the first finger, this is field, it's going to point where the fields are pointing like this, and second finger, this is current. Yeah, this is current, and thumb is motion. So the thumb is going to tell you in which direction is the conductor going to. So like this one, if I'm placing my paper like this, the fields will be pointing that direction from the north to the south. So I'm going to place this first finger, this one here, in the direction of the field, and this second finger here will point where the current is going. You can see current is moving this direction, in this direction. So I'm going to put this. Then you can see the thumb is pointing up. Yeah, it's pointing up, which means that the conductor is going to experience an upward force according to Fleming's left-hand rule. So you can see you're going to use this one. This is the first finger, second finger. First finger is field, so the field is pointing this direction, so I'm going to put it like that. Then this second finger is pointing where the current is moving to. Then this one is pointing upward. You can be able to see that. So we are going to say it's going to experience an upward force. So we can be able to say this is an upward force. Yeah, upward force. Yeah, so an upward force. So if you're new to Proflan YouTube channel, consider subscribing so that when I'll be doing more of these tutorials, you'll be notified. So the effect of this experiment demonstrate, this is what we have repeatedly said it, this is what we call mortar effect. Mortar effect is a phenomenon where when a conductor that is carrying current is placed in a magnetic field, that conductor is going to experience a force, and that's what we call mortar effect. The student replaced the battery with a low frequency alternating current. Then the student closed the switch. Describe the movement. Yeah. of the wire will vibrate up and down. Because this is we are talking about alternating current, it will mean that the current will keep on changing direction. So in that way, this particular wire is going to experience forces which are constantly changing direction. So for that reason, it's going to vibrate. Since current, that is AC, we are talking about AC, keeps on changing direction. Since it keeps on changing direction, also the forces will be changing direction due to varying magnetic fields created. Alternating current creates magnetic fields which are constantly changing direction, and that's why we're going to say that. Complete the following sentence by drawing a ring around the correct line in the box. Once the coil is spinning, one side of the coil is pushed by a dash and the other side is pulled, so the coil continues to spin by a force. Because the coils are inside a magnetic fields, because these are magnets, we are having magnets here, these are magnets. So since they are magnets, then we are going to have magnetic magnetic fields. And since there are magnetic fields and there is a current flowing through the coil, there is going to be a force due to motor effect. So that is exactly what we are going to say. Now suggest two changes to the electric motor that will make it faster. So increasing current, or using stronger magnets. Suggest two changes will make the coil spin opposite direction. Reverse direction of current, or reverse the poles of the magnet. So any of them is going to change the direction of this force. State ways in which the force can be increased already. For number 8, I want you to write the answer in the comment section. I want to check whether you can be able to earn the marks. Yeah, ways in which the force can be increased. I want you to write the answer in the comment section for number 8. This is your homework. Number 8. State which in which the force can make opposite direction. Right, for number 8b, also write the answers for this. Yeah, this is your homework. In what circumstance will no force? In what circumstance will there be no force? Can say when. Yeah, I want you to write in the comment section what's the answer for number 8. In what circumstance, yeah, will be there no force? When the conductor is parallel to the magnetic field. So what is the answer for this one? B. And what is the answer for A? Yeah, just I'm going to check in the description, in the comment section, so that I can be able to mark for you this section. Guys, if you found value from this particular video, consider subscribing so that anytime I'm going to do more tutorials, you'll be notified. So don't forget to check our Patreon page so that you can be able to access the PDF of this particular paper that we were having at this given point. See you in the next tutorial.